Alright, so we're back. So sorry about that last example. Remember this nightmare? Alright, our long national nightmare is over. Alright, another way we can find a partial derivative and is by substitution. So let's say w is a function of x and y right here. And they ask us to find the partial by substitution. Well, they're telling us x is this s squared plus t squared, and this y is this st to the negative 1. We want to find the partial of w with respect to s. So this is would be like a partial derivative for us. We can do this, solve this by substitution. In other words, I can say w is 2, replace my x, this becomes s squared plus t squared times y, which is this st to the negative 1. And to make it easier for me, I'm going to go ahead and distribute. We will get 2 s cubed over t plus 2 st. And if I want to find the partial of w with respect to s, well, it's not too bad now. Don't worry about the t, they're just a constant. We would just get 6 s squared over t plus 2t. And if I want to find the partial of w with respect to t, again, be careful. T is my variables on bottom. So remember, the derivative of 1 over x is negative 1 over x squared, right? So this should just become negative 2s cubed over t squared plus 2s. All right. Ta-da! That was it. All right. No, I promise you they're not really all that bad. The really hard one is something like, is this one. So let's just kind of look at another example of a chain rule. So let's say w, which is again a function of x and y, is equal to, let's just say, x squared y. And I say x is equal to, let's do e to the t squared, and we'll say y is cosine t. Okay? So if I want to find the derivative of w with respect to t, so we want to find the partial of w only with respect to t. The derivative of d with respect to t there. Oops, sorry. It would be the derivative itself, not a partial. It's not a partial because it's the actual derivative itself. So my rule, and we're going to do these all in our head, my rule is very simple. I'm going to take the derivative of w, this is what I do, the derivative of w with respect to x, that's my variable, and then my x is being replaced with this e to the t. So now I've got to take the derivative of x with respect to t. Now these are partials. See, w is a partial because w is in terms of x and y. That's why we use the partial notation here. The del's here. But when I take the derivative of the inside, x is only a function of t, which is why we use our old rule notation, dx dt. And I just do the same thing for the y's. The partial of w now with respect to y times dy dt, because y is a function of t. And you're going to do this in your head. This is, dw dt, and do these in your head. Okay? The partial of w with respect to x. Well, that's just 2xy times the derivative of x with respect to t. Chain rule, we get e to the t squared times 2t. Plus, this is your derivative. The partial of w with respect to y, which is just x squared, times the derivative of w, which is negative sine of t. And you can leave it like this, and that's fine. Now, or you can sub in for x and y. It's not much, but you would get this then. 2 e to the t squared times cosine of t times e to the t times t squared, 2t, plus x squared, which is going to be e to the 2t squared times negative sine t. And that would be your actual derivative. If you were to substitute these in, and you did the old-fashioned way of derivative, that's what you would get. That would be your derivative with respect to t. And you can verify that by substituting this in. If I said w of t then would be, this becomes e to the 2t squared times cosine of t. And if you take this derivative using our product rule and chain rule, you would get, of course, you would get that. All right. Excuse me. So anyways, I hope you guys enjoyed the video, and I'll see you guys later. Bye-bye.